Good morning. I'm Farzam Toudeh-Fallah, R&D Director, Quantum Communications at Ciena. What I'm going to discuss in this presentation is our pragmatic perspective on the development of quantum-secured optical networks. In order to do so, first I'm going to discuss and propose a series of requirements for deployment of such networks in real-world operational environments. And I would like to emphasize on these 4 words, real-world operational environment. These 4 words will constitute the foundation of my presentation here. Once I establish this set of requirements, then I would proceed to discuss our approach towards deploying these networks on two distinct type of approaches, terrestrial and satellite-based. So in terms of the requirements, Ciena is a networking system services and software company and is a pioneer in advancing communication systems. As such, we have been already engaged in quantum communication for years now, since we believe that quantum is the next frontier in advanced technologies. Our focus in the area of quantum communication is on security. In other words, establishing quantum secure channels. So in terms of terminology, what we define as a quantum secured channels are those channels that are secured by principles of quantum mechanics, i.e. we utilize QKD to establish these quantum secured channels. The figure here depicts what we demoed at the last OFC conference in San Diego. As depicted here, we utilized one of our flagship products, the Wave server, and we paired it up with the Toshiba QKD system. Using this methodology, we were able to quantum secure an 800 gigabits per second channel at the OTN layer. And then we also used another product. We have 8140, and we paired it up with an ID Quantic QKD system, and using that, we were able to establish 400 gigabits per second quantum secure channel at MACsec layer. Then, as is shown at the bottom of this figure, we basically took that 400 gig MACsec, quantum secured MACsec channel, passed it through the Wave server. Wave server took that channel, multiplexed it into that 800 gig quantum secure channel at the OTN sec, and sent it to the other side of this exhibition floor. And then the reverse process took place, so we were able to establish a quantum secure channel end-to-end at 2 different layers. Now, as discussed by the previous presenters, one of the main limitations of QKD in today's systems is the distance limitation. So at this point, in terms of the practical systems based on the requirements that we set in place and providing an acceptable secure key rate, the maximum distance, give or take, is around 100 kilometers for deployment. Now, the question is, how can we increase this distance? One approach that is available today is called trusted node, and that's what we demoed during this demonstration at the OFC, and that's right in the middle. You might notice that in the trusted node, 2 QKD systems are placed back to back. The first QKD system receives the key, the session key, and then it converts it from quantum to digital format, and then it passes it to the second QKD system, which, and again, in that one takes the key, session key from it converts it from digital to quantum again, and sends it to the next QKD system at the far end. This is how you can increase the distance, and basically using this methodology, you can go for thousands of kilometers. However, there is a catch, and the catch is that once the key is converted from quantum to digital, right at that moment, it's vulnerable to eavesdropping. So the question is, how can we basically establish a long-distance quantum communication channel such that we can distribute the key end-to-end all through these quantum channels? So in order to do that, first we need to take a look at the set of requirements. What we're looking at here on the top is a regular optical channel. An optical channel, the long-distance channel, consists of two sites, sites A and site B. These sites could be thousands of kilometers apart. We break them down into multiple spans, shorter spans of 80 to 100 kilometers each, and then each span is connected to the next via an amplifier. These amplifiers are located in stations. We call them ILA, stands for inline amplification stations. And now, because of the no cloning principles in quantum mechanics, the whole notion of amplification doesn't even exist in quantum communication. Therefore, the equivalent of this model in quantum communication is a quantum communication link, as depicted down at the bottom of this figure. So a quantum communication link consists of quantum channels specified with the letter epsilon and quantum repeaters specified with the letter psi. So each span of this quantum communication channel is connected to the next one via a quantum repeater. As the first requirement that we impose on the deployment of these quantum communication channels in the real-world environment is that these quantum communication channels must use the same infrastructure that is deployed today. We cannot have a dedicated quantum communication channel because it's not economically viable. So the question is, how can we do this? Okay, the first question goes back to those ILA stations because, as I said, if you're going to use the same infrastructure, which means the same fiber and the same ILA stations that are deployed today, question is, okay, what can we expect from those ILA stations? Well, these are the typical ILA stations out in the field. They are about 10 by 15 feet in terms of the size, very limited in power and space they can provide to the telecom equipment. And the best they can do is that they can just provide some air conditioning in terms of the cooling, and that's it. So based on all this, now, it becomes even worse when we go and discuss submarine cables. So a major part of our business is developing modems for submarine cables. We have modems that can launch optical channels into submarine cables in excess of 10,000 kilometers. Matter of fact, there is one of those cables right in the middle, the red one, if you can see it. That is the one that connects Los Angeles to Melbourne, Australia. That's at the distance of 13,500 kilometers. And recently, we were able to launch a 1 terabit per second optical channel into that link. So obviously, the question is, how can we quantum secure that channel with such a long distance? Now, these submarine cables are supported by submarine repeaters, as depicted in that photo. These submarine repeaters are about 20 centimeters in diameter and about a meter in length. So the space is extremely tight. So imagine quantum repeaters should be able to be placed inside these repeaters. So based on what I've discussed so far, these are the set of requirements that we are imposing on deploying quantum communication channels. So number one, with regard to the fiber optic medium, we require that quantum channel basically coexist with the optical channel on the same fiber. In other words, we want to multiplex quantum channel and optical channel on the same fiber. Usually it's done by running the optical channel, the data channel on the C band and quantum channel on O band in order to have enough guard band between them to avoid any Raman scattering. The second requirement is that all degradation factors must be taken into account for real-world environment when we take into account the fibers. Also, in terms of the quantum repeaters, we are requiring support for at least 100 kilometer spacing between the repeaters, based on what I discussed. Also, we cannot expect any dedicated sites for quantum channels, as I pointed out. They have to use the same ILA stations. And also, these ILA stations are extremely limited in terms of the power and space, so that's something we have to take into account when we design these quantum repeaters. And also, absolutely no cryogenic environment available in these ILA stations. We are requiring at least 40 degrees centigrade ambient temperature tolerance for quantum repeaters. So these are the set of requirements that we are calling for the development of quantum repeaters. So with this set of requirements, now I'm going to talk about, I'm going to provide some technical discussions on our approaches towards establishing these quantum secure channels. The first one is terrestrial approach. This is Ciena's vision on establishing long-distance quantum secure channel and large-scale quantum optical networks. These quantum optical networks will be able to support end-to-end quantum secure channels. As depicted in this figure, the sites in this quantum optical network could be thousands of kilometers apart. These sites are, the way we envision this network is that we multiplex quantum and optical channel based on the requirement that I discussed before and launch them into the same fiber. Once they hit one of these devices that we designate as quantum optical repeater system, or QRS, then we demultiplex the optical and quantum channel. We route the optical channel over an optical element and route the quantum channel over a quantum repeater. And then we multiplex them back, send them to the next one and the next one until they arrive at their destination. Now, the optical element could be a ROADM, could be an amplifier or a switch. We know very well how to build them. We've been building these devices for decades. Obviously, the question is on the bottom part of this device, the quantum communication link. The quantum communication link consists of two parts, as I pointed out, the channel and the quantum repeater. The model that we are looking into, in terms of first I'm going to discuss the model for the quantum channel. Based on the Stein-Spring dilation model, basically the quantum channel is modeled as a unitary transformation of a joint system and the environment states. Now, for optical fiber, usually the unitary transformation is of a type Gaussian unitary, which means it is based on a bosonic quadratic Hamiltonian in field operators, as depicted here. So one can then proceed and derive the operator sum model, which would be based on the cross operators. Now, up to this point is acceptable by us. The problem arises when researchers try to adapt this model towards the real-world optical fiber. In their adaptation process, they consider an optical fiber a purely lossy environment, which is incorrect. Why? Because we know very well that there are other degradation factors that contribute towards signal degradation. So, in addition to loss, we have SOP fluctuations, there is dispersion, nonlinear effects, and Raman scattering, which are especially important when we talk about the coexistence mode. And remember, that's the mode that we want to launch these channels. So, for instance, in the terms of the SOP fluctuations, our studies have shown that we can expect upwards of 5 megarats per second SOP fluctuations in aerial fiber. So if we launch the quantum channel into an aerial fiber, then we can, and it is lightening. The lightening have a negative impact on quantum channel upwards of 5 megarats per second. So these are the degradation factors that we have to take into account, and we are working on this model. Now, in terms of the quantum repeater model, this is the model that we are considering for our vision. It is based on the familiar entanglement-based model. It is very well known in the industry and academia. So in this model, again, this model is based on entanglement sharing. So each quantum repeater in this model basically establishes entanglement with its own neighbors. And then they go through this process called entanglement swapping, which is a nested process. Obviously, I don't have time to go through that details, but once this process is complete, at the end of this process, two sites, sites A and site B, which might be thousands of kilometers apart, At that point, site A will be in entanglement with site B. Please notice that when we started this process, site A was not in entanglement with site B. Once they are in entanglement, then we can use the quantum teleportation process to basically transfer the quantum state from site A to site B. Now, for quantum secure channel, we have another option in addition to teleportation, and that's using the native QKD protocols such as E91 or BBM92 to establish these quantum secure channels. But please notice that this mechanism, in terms of the application, it doesn't matter whether you want to run QKD over this or distributed quantum computing, it doesn't matter. Now, we know very well that there are serious challenges regarding this model, including development of quantum memories, increasing coupling efficiency, achieving high fidelity, achieving high entanglement generation rate, and so on and so forth. Now, let me just mention that there is also another approach taken by researchers known as one-way quantum repeaters. In this approach, basically each quantum repeater will compensate for both link and operational errors by using quantum error correction. Well, in theory, this is an appealing approach because using this approach, there would be no need for quantum memory. Okay, very well. However, this approach suffers from a major limitation, and that limitation is the 3 dB loss tolerance threshold. Now, if we translate this 3 dB loss tolerance threshold into the fiber propagation, it would be equal to a maximum of 15 kilometers on C-band, or even worse, 8.6 kilometers on O-band quantum repeater spacing over NDSF fiber. As I pointed out, our requirement calls for 100 kilometers. Therefore, based on this, a one-way quantum repeater is absolutely unacceptable for deployment, and we reject it. So, and this would also goes for repeater graph states, or models that I don't have time to discuss. So, now, why am I emphasizing on this, the fact that we are rejecting this 3 dB? Because I'm going to show you again, real-world environment. This is the real-world optical link between New York and Chicago. So this is about 2,600 kilometers in distance and about 31 ILA sites. Okay. Now, let's take a look at the loss per span. You can see the loss per span can go upwards of 28 dB, and this is just in C-band. Again, we would like to use quantum channel on O-band. So if I translate this to O-band, you can see now we are looking at loss upwards of 42 dBs per span. So that's why the quantum repeaters should be able to tolerate this much loss per span. Now, we have also conducted some analysis on the required secure key rate or required SKR. It plays an important role for designing these quantum secured channels. Based on our analysis, aggregation of traffic into higher channel capacities would help dramatically in terms of reducing the RSKR, required SKR. As shown in this figure, this impact would be specifically pronounced in CNL type of propagation, because and more we are seeing our customers are moving from just C-band to CNL, C plus L band kind of a traffic. Now, in terms of achieving quantum repeaters, based on what I described, we are looking at a very long, time horizon. Now, don't get me wrong, you talk to folks in academia, you talk to folks in startups, and they would claim to have a quantum repeater in the lab. However, based on the set of requirements that I discussed, in order to deploy these quantum repeaters in the real-world environment, we are looking at a very long time horizon. That's why, at the same time, we are taking another approach, and that's satellite-based. In satellite-based, as is depicted in this figure, a satellite in space will establish a quantum channel between the ground station. So, using this methodology, a satellite can distribute the key between the two ground stations. Now, Once the two ground stations basically gain the same secret keys, then they can use those keys to establish quantum secure channels on an optical fibers. Now, we are engaged in the Quantum Encryption and Science Satellite, or the KeySat project. This project is a 5-year research project sponsored by the Canadian Space Agency and is administered by the IQC at the University of Waterloo. We are a member of a consortium consisting of 11 academic institutions, industry partners, and the government of the Canadian government. And we have Ciena has a very specific role to play in this project. This is our role. So we will deploy our wave server platform inside these quantum ground stations. And then once the key is generated by the satellite using that box, specified as quantum transmitter receiver, then our wave server will establish an Etsy API channel with that quantum communication box and will receive the key. Once the two wave servers on the two ground stations receive the same secret key, then they use the key to establish a quantum secure channel on that fiber link between them, up to 800 gigabits per second per channel today, and very soon we will increase it to about 1.6 terabits per second using WaveLogic 6. So again, this is a 5-year research project. Our goal is to understand how we can interact with the satellite, because today, when we interact with QKD systems such as ID Quantic manufacturers and other manufacturers, we know exactly what we can expect in terms of the SKR, or secure key rate, because it's constant. However, when we try to interact with the satellite, it won't be deterministic. It would be completely stochastic, because if the satellite shows up over the station and it's cloudy, it has to pass. So we need to know how we can interact with the satellite, what would be the expectation, and the statistical models. So with that, I'm going to wrap up with such closing remarks. So basically, we set forward a set of requirements for establishing long-distance quantum communication channels. And I talked about the limitations in the quantum channel models we're facing, in quantum repeaters that we're facing, and so on and so forth. Especially, I mentioned about that 3 dB limitation in one-way quantum repeaters is absolutely out of the question right off the bat. And then I presented our Ciena's vision on establishing long-scale quantum optical networks that are capable of supporting end-to-end quantum secure channels. We have published this. It's on archive. You can read it, take a look at it yourself. As I pointed out, Ciena is already engaged in the KeySat project, in the satellite quantum communication as a parallel approach to quantum repeaters. And the last point I would like to make is that we welcome collaboration with academia and industry towards basically developing a pragmatic approach towards developing these long-distance quantum secure channels. So with that, I'm going to wrap it up, and thank you so much for your attention.